Hello, I am Yuta Noma from the University of Tokyo, and today I would like to talk about our new paper, Pop-up Print, Rapidly 3D Printing Mechanical Reversible Objects in the Folded State. First of all, 3D printers are used widely in entire the world as a powerful tool to enable the vision of rapid prototyping. However, 3D printers have three problems. First is print time. 3D printers print the object layer by layer, which results in longer print time for a taller object. Second is support consumption. To print overhangs, 3D printers use support material. However, they will be thrown away after printing. Third is storage and transportation. Most 3D printed objects cannot be transformed into the compact state, which is an obstacle for storage and transportation. To cope with these problems, many researchers have proposed various projects. For example, 4D printing methods such as thermorph, shape representations using springs, and structures inspired by telescopes. However, they suffer from irreversible and complicated transformation processes, or extreme limitations on the final shape. To provide a better solution, we refer to the development of the beetle horn. The beetle horn is first developed in the folded state and is unfolded after metamorphosis. By other words, they fabricate their horn in the folded state and unfold them after fabrication. Inspired from the beetle horn, we propose pop-up print, a method to 3D print objects in the compact folded state and unfold them after printing. We first show the object printed with our technique. They are printed in the compact folded state like this. After 3D printing, the object can be unfolded like this. These objects are the Japanese safe bottle and cup and can be used as a portable drink set. Also, we printed various objects such as this cup-like object, the Huffman's cone, the two-hump dome, the starfish which has a branched arm, and the Stanford Bunny. To fold various objects, we made the following three contributions: the method to fold various 3D shapes, the mechanical bistability measurement, and the interactive design tool to determine the final crease pattern. First is the folding method. We refer to the related work in computational origami that uses planar folding. Planar folding is a folding method that folds the 3D surface with a plane, just like the left figure. We applied planar folding as the basic folding method because its structure is simple and the computation method is very easy. Here we show the folding pipeline. First, we extract the surface of the original shape. Second, we extract the foldable region. Third, we fold the surface with planar folding. And last, we thicken the surface and create the hinges on the creases. For detail, please refer to the paper. Next, for a second contribution, we conducted a mechanical bistability measurement experiment. Mechanical bistability means that an object becomes mechanically stable both in the folded state and the unfolded state. As we show in this video, the left is bistable while the right is not bistable. Since the object will be used in the unfolded state, it is important to make the object mechanically bistable. To generalize this mechanical bistability, first we 3D printed the example objects by changing the shape parameters. Second, we measured the force required to fold the object from the unfolded state. This slide shows the result. By curve fitting, we obtained the formula that can calculate the mechanical bistability with several shape parameters. Using this formula, we can judge whether the object becomes bistable or not. Finally, to utilize the methods, we implemented an interactive design tool to determine the crease pattern. First, users can manually rotate the object and find the best folding direction. The red area is the foldable region, and the foldable region changes when the user manipulates the slider. Also, the design tool computes the bistability using the formula, and if it is not bistable, the design tool notifies the user by showing the area red. Finally, the user can thicken and save the 3D model for 3D printing. So, my conclusion is the following points. First, we propose pop-up print, a method to 3D print objects in the compact folded state and unfold them after printing. Next, to achieve pop-up print, we made the three contributions. Thank you for listening.